All right, let's come back to uh, the introduction to 5, 4G and 5G cellular network. And this is the second hour of our lecture. So previously we talked about frequency to use. Now we are going to continue from there. Okay, so uh, problems with smaller cluster sizes. As you can see, if we have a large cluster size, that cluster size will separate the same frequency cell far away. So for example, if we look at this gray cell, its neighbors is here, its neighbors here, its neighbor here, its neighbor here. So you can see that sort of two cells away from each other. Each one has the same thing. For example, this purple one, it has uh, two cells away. And if we use a smaller cluster size, you will see that this is like one cell away, and this is like one cell away. So as a result, you get things that are closer to each other, and then it will interfere, more severe interference. So it's the same. If we look at the purple ones are closer to each other and then it interfere with each other more closely. So that's the smaller cluster size. Okay, and then how will we characterize frequency to use? Let's make some notations. The first D is the minimum distance between centers of cells that use the same band of frequencies, called channel. We call it called channels. Then R will be the radius of a cell. D will be the distance between centers of adjacent cells. So uh, D will be R R multiplied by square root of 3. How come? Because we separated into a hexagon, and by geometry, we know the distance of the center will be the distance between centers will be square root 3 of the r. So we can actually do the calculation by geometry, but we don't uh, do the details here. So the distance between cells will be uh, r multiplied by square root of 3. And then n is number of cells in repetitious pattern. This is called the reuse factor. Reuse factor. And each cell in pattern uses unique band of frequencies. So if we need to illustrate this, this is R, this is the D, that's the distance between centers. And capital D is the centers among co-channel cells. The centers, the distance of centers among between co-channel cells. Okay, so we have a hexagon cell pattern following values of n possible. So n will be uh, I squared plus j squared plus I multiplied by j. And this is the number of sort of the index of the cells. Then the possible value of n will be 1, 3, 4, 7. And d divided by r will be square root 3 of n. D divided by small d will be square root of n. That will be from this structure. And that's a reuse factor. Then what would be the minimum distance between centers of two cells with the same band of frequencies? If cell radius is 1 km and the reuse factor is 12, then we just put it into the equation, and we get B over R will be square root 3n, and then 3 multiplied by 12, take the square root, multiplied by 1 km, that would be 6 km. So as a result, the minimum distance between the centers of two cells with the same band of frequency will be 6 km. So if we look from the scratch, mobile radio telephones are used for military communications in early 20th century. As we mentioned before, the mobile phones are very expensive, very costly, and very limited at that time. So they are only limited to high priority use, which is government or military, those things. It's not for commercial operations. Then the car-based telephones first introduced in the mid-1940s. The reason being that the power system, the battery system was not that advanced at that time. So a car has a large battery. So the telephone at that time has to take the power from the power of the car. That's why it was first introduced by car-based telephone. Then it's a single large transmitter on top of a building. Single channel used for sending and receiving. It was all very simple at that time because we are not considering multiple users, multiple access, channel reuse. We don't consider those things at that time. So single transmitter, single channel. And to talk, use a push a button, enable transmission and disable reception. Become known as a push to talk because you have to push a button before you talk. So that's a push to talk in the 50s. And that's a citizen CB radio, taxis, police cars use this technology. And then in the 60s, uh, there was a IMTS, improved mobile telephone system. Use two channels, one for sending, one for receiving. If you see it here, you have to enable transmission and disable reception because they are now duplex. You have to transmit at one time instant and then receive at another time instant using the same channel. Then it uses two channels for IMTS. No need for push to talk because you use it simultaneously. Then it used 23 channels from 150 megahertz to 450. It was not that efficient at that time because this is a large band and it accommodates only 23 channels because the filter and IC technology was not that advanced at that time. So it's from the perspective of nowadays, it's actually a waste of resource. In other words, we want to accommodate a lot of channels within this small band of frequencies. Then the first generation cellular advanced mobile phone service invented at Bell Labs and first installed in '82, and it's used in England, and that's called TACS, TACS, and Japan, that's called MCSL1. Then the key idea is it's exclusively analog analog. And the geographic area is divided into cells. Geographic area is divided into cells. Typically 10 to 25 kilometer. And you know that by using a large cell like 10 to 25 km, the channel don't get to be reused very efficiently. As a result, we're wasting a lot of resources in frequency. As you can imagine, if we use 10 to 25 to cover a cell, and the frequency don't get to be reused in such a large area, we will not be able to cover a lot of users. And it's definitely not going to work in today's network. And cells are small, of course, from the perspective of that time. From nowadays, these cells are large. Frequency reuse is exploited in nearby cells. So it was the first one to introduce frequency reuse, although it's not that efficient. And then, as compared to IMPS, could use 5 to 10 times more users in same area by using frequency reuse. Divide area into cells. Smaller cells are also require less powerful, cheaper, smaller device. The reason is that if you have a large cell, imagine this, what do you need for a large cell? You need a more powerful transmitter and receiver, because for a large cell, the distance is going to be large. So you need more power, right? And then the device will be larger. The antenna size will be larger. Then it demands more high-end equipment, right? So you can imagine as time goes on, the new system is getting smaller and smaller in terms of uh, the size, the form factor, the power, and everything. It gets smaller and smaller. Okay, so the AMPS Advanced Mobile Phone System, that's a first generation analog system for North America. We have two 25 megahertz bands allocated to AMPS. The forward direction is BS to mobile unit, which A69 to A94 megahertz. The reverse, which we call it up communication, is mobile to base station. It's A24 to A49 megahertz. In each market, two operators are accommodated, and each operator is allocated only 12.5 megahertz in each direction. Channel spaced 30 kHz apart. It's 416 channels per operator. You can imagine that 416 is large at that time, but it's considered very small nowadays, because we accommodate thousands of people at the same time in a cell. Right? We accommodate multiple, even tens of thousands of people. Okay, and 21 control paging access and 395 traffic channels. And each code uses two traffic channels. So forward equal to reverse plus 45. So that when you get a forward channel, you know where the reverse channel is. they are related by this equation. And then control channels are 10 kbps digital channels, and traffic channels are analog using frequency modulation. So the cell design, this is briefly mentioned before. We have F, for example, this called F. Cells are grouped into a cluster of 7. So we have 1, 2, 3, 4, 5, 6, 7, and that's a cluster. And then we have another cluster which has the same set of channels and same set of structures. So from A, B, C, D, E, F, G, A, B, C, D, E, F, G, and it's a cluster into a cluster of 7. Then the later indicate frequency use. So A uses the same set of channels. For each frequency, about of 2 cells is used before reuse. So for each frequency, then the 2 cells are used before reuse. So it's reused by the same data. To add more users, smaller cells are used. The reason is that, let's say you have 1,000 people inside a cluster. If you put it into 7 cells, then you can imagine that each cell controls around 130 to 140 users. If you use large cells, then the number of cells is going to be smaller. Then each cell has to manage a large group of people. So to add more users, we tend to use smaller cells. That's called microcells. Then frequency may not need to be different in CDMA. So frequencies may not need to be different in CDMA, meaning that in CDMA system, users are associated with so-called code. That's orthogonal codes. So frequencies may not need to be different because users are separated by their code, not frequency. Okay, and then cellular network organization by cell design around 10 miles radius, served by base station consisting of transmitter, receiver, and control unit. Base station antenna is placed in high places. As you can imagine, if the antenna is not in high places, what problem do we have? If an antenna is not in high places, for example, churches, high-rise buildings, it will be shadowed, right? It will be shadowed by, for example, buildings, trees, obstacles, mountains, those things. They will shadow the EM wave, so the transmission will not be smooth. So that's why we need to place it in high places. And then operators pay around $500 for base station location installation. That's like a rent, right? Pay a rent. Of course, the price will differ from time to time, from region to region. From country to country will be different. And 10 to 50 frequencies are assigned to each cell. Cells set up such that antennas of all neighbors are equidistant, hexagon. So let's say hexagon is the only geometry that fills the space perfectly and repeats itself. Of course, it's an idealistic way of thinking about this. In reality, it may not be, as we mentioned, in reality, it may not be the case. But uh, ideally, we need to sort of put a model on it so that we can analyze and design it. So that's called, that's the way we put it, hexagon. Then in North America, two 25 MHz bands allocated to AMPS, one for transmission from base station to mobile unit, one for transmission from mobile unit to base station. So approaches to increase capacity, adding, reassigning channels. Some channels are not used. So one way is we add or reassign channels. When some channels are unused, we use it more efficiently. The other thing is frequency borrowing. Frequency are taken from adjacent cells by congested cells. So let's say if you have a cell that is very congested, so for example, this cell is very congested, a lot of people go into this cell, then what's going to happen is that it's running out of its own frequencies. Then what can it do? It can borrow, for example, this neighbor E, it has very few users. It has a lot of channels that is not used by its users. So that F can communicate with E and then say, hey, how about you let me use your channel? So some of the channels will be borrowed for F to serve F users. So that's called uh, frequency borrowing. You borrow frequencies from adjacent cells. Of course, the condition is that uh, the cell is congested. If it's not congested, then there's no need to borrow, right? So it borrows only if it's congested. Then the next thing is cell splitting. Cells in area of high usage can be split into smaller cells. So, for example, if F is congested, then it can split into two cells. Then the channels and allocations can be reallocated, redesigned. We now have some flexibilities in terms of those things. So cells in high use can be split into smaller cells. And microcells antennas move to buildings, hills, and lampposts. So we have more flexibility. We move, as long as the power supply is sufficient, we have more flexibility. We just put the antenna to building hills or lampposts so that it serves the area better. So there are also other issues such as security issues. The 1G system is the analog cellular phones. Of course, it's insecure. The reason is that anyone who can survey the frequency used, for example, you use a uh, oscilloscope or network analyzer. You analyze the frequency, you know which frequency is in use, then you tune your receiver to that frequency. it's not encrypted. It has no security, uh, any security. Uh, it does not have security design. So as long as you tune your frequency to that frequency, and then you get to receive what people are talking in that frequency. So that's a security issue. So it's insecure. Anyone with an open radio receiver can listen. And also type of airtime. Open radio receiver connect to a computer and record 32-bit serial number and phone number of subscribers when calling. So once it's recorded, then it can even driving around and collect a lot of serial numbers, and then they can reprogram the phone and then resell them. So there's sort of uh, steal your cell phone number, and then use your number to communicate. And then of course the bill is gonna be billed to you instead of the thief. And then the second generation cellular is based on digital transmission. So it's kind of different approaches in US and Europe. In the US, it's more diverged. Only one player in 1G and becomes several players in 2G due to competition. And survivors are IS-54 and IS-135 because they are backward compatible with MPS frequency allocation, and then the dual mode, and then IS-95 uses spread spectrum, which is the CDMA system, and Europe has more convergent uh, system, five incompatible 1G systems without clear winner. European PTT development of GSM uses new frequency completely digital communication. So here is the cellular architecture. Uh, Here we'll have a subscriber identity module, and then mobile equipment, and it connects to the base transceiver station. So here is a connection between your device and also the base station, and this is of course a fixed station in uh, a fixed station on the ground, and this is the mobile one. So this is a mobile station subsystem, and then base transceiver station. This whole thing is located in the base station subsystem, and then also this base station controller, base station controller, and base station controller, and then it connects to the controller, and then the controller connects to the network subsystem. And as we mentioned before, there will be a fixed LAN 9 communication, which is the PSTN, and it connects to mobile service switching center. And we have talked about HLR, location registration, and VLR registration, location registration, and then this switching center, and then you have authentication center, identity registration. All this is done for security issue, also for accounting issues. For example, how much time have you talked on the phone? How much time do you spend on communicating with people so that they can charge a proper fee to your number. So done by those things. So here is the mobile station, which includes this, and then the base substation, which includes this, and then the network substation, which includes this. Okay, and here is a picture. Here's a picture, and as you see, you build a tower that's high rise above the ground, and then put antennas on it, and then the antenna is connected to a power or information cord, and those cords goes in down on the ground and then goes to the base station. Sometimes the base station servers are also collocated with the antenna. So the cellular architecture has a base station controller and base transceiver station, and one BTS per cell, as we mentioned before. And then one controller, base station controller, can control multiple BTS, and it allocates radio channels among BTS, so that, as previously mentioned, some of the channel operation, for example, channel borrowing, can be done by controller. If a controller knows that cell A is congested, cell B is more empty, then he can put cell B's channel to the use of cell A, so that is called channel allocation. And it manages call handoff between BTS. So for example, if you go from cell A to cell B, then the control knows it. It knows that your signal is going stronger and stronger to cell A, then he can do the handoff for you. And then controls handset power level, which means that if you are further away from the cell, not from the cell, from the base station, then it will increase your power. So I think it's a very important concept. Let's say your location is further away from a base station, then the controller knows about this. It needs to increase your power so that you can communicate well with the base station. If you are closer to the base station, then it will ask your cell phone to lower the power, because you have been very close. Then there is no need to increase the power, right? So that's the reason. So the power can actually be adjusted by the distance, and it's all done by the controller. And then the next thing is the mobile switching center. It connects to the PSTN, which is the LAN 9, and switches codes between BSCs. It provides mobile registration, location, authentication, accounting, so on and so forth, and contains equipment identity register so that you can identify your cell phone. The home location register, visitor location register provide call routing and roaming. So let's say if your home location is at cell A and you go to cell B, then now you are a visitor in cell B, so that it reroutes all your information to cell B, because you have been considered to be located in cell B, right? So that's called call rerouting. If the call is still routed to your original cell, which is cell A, then it does not get to your mobile device. Think about it, right? Because it goes to cell A, but you are not in cell A, then the communication will be lost. So that's called port rerouting and roaming. And then VLR, HLR, and MSC functions are generally in one equipment, but with the advancement of the IC and the computer and the cell phone technology, now we can put everything in one equipment. So equipment identity register contains a list of all valid mobiles. Then the authentication center stores the secret keys of a SIM card, so that when you want to communicate, it will authenticate by the secret keys and verify that oh, indeed this communication comes from comes from the authentic authentic user instead of arbitrary person, right? Arbitrary person. Okay, so uh, the equipment identity register contains a list of all valid mobiles. So that what that means is it needs to identify who is calling and who is communicating, so that it helps to calculate the minutes, the time, and then the next step is going to be able to do the accounting and charge the fees, and how much you have to pay for your mobile, your communications. And then the authentication center, AUC, stores the secret key of the SIM card. And then each handset has a International Mobile Equipment Identity, IMEI number, so that it's unique. And then once you get the IMEI number, it will uniquely identify your mobile phone. And then advantages of digital communication for wireless. It's uh, voice, data, and fax can be integrated into a single system. And then better compression can lead to better channel utilization. And error correction codes can also be enabled, so it be used for better quality. And so sophisticated encryption can be used for digital as opposed to analog systems. And difference between the first and second generation system is digital traffic channels. First generation systems are almost purely analog. Second generation are digital. So it has the advantage of, for example, encryption, error correction code, and things like that. And then encryption, all second generation systems provide encryption to prevent eavesdropping. Then error detection and correction. The second generation digital traffic allows for detection and correction, giving clear voice reception. And of course, all those advantages moves on to 4G and 5G. Except that the technology may be more advanced, the algorithm may be more complicated, but uh, the general concept has not changed. It still does the encryption, it still does the error detection and correction. And then channel access. Second generation systems allow channels to be dynamically shared by a number of users. Then integrating data over cellular, the direct access to a digital channel, and voice and data using one handset. So for example, GSM PCS 9.6 kbps, 14.4 kbps, packet mode specified, short message service, IS-95 based CDMA 13 kbps, circuit switching, and packet mode specified, show message service. And the GSM Global System for Mobile Communications. The GSM systems completely designed from scratch, not backward compatible. And this is generally in the 2G to 3G system and uses 124 channels per cell. Each channel can support 8 users through time division multiplexing. Some channels used for control channels and several flavors based on frequency. For example, GSM 900, GSM 1800, and that's called DCS 1800, or GSM 1900, that's called DCS 1900, which is generally used in North America. GSM 1900 phone only works in North America. So, for example, if you, in the old times, if you move from one country to the other, you have to buy a new cell phone or you cannot use it. In Europe, you can transfer your SIM card to a phone of the correct frequency. This is called SIM roaming. And GSM radio link is 890 to 915 MHz uplink, 935 to 960 MHz downlink. Uplink meaning from user to base station. So you need to recall the cellular framework that we talked about previously. Uplink is the link from user to base station. Downlink is the data transmission from base station to mobile user. And 25 megahertz is 124 multiplied by 200 channels. So it has 124 channels, each with 200k hertz. Each channel is TDMA. Remember the time division that we mentioned before? It's divided by time, meaning that each user is using the same frequency with the time slot. Then the next one is using the next time slot, so on and so forth. That's TDMA with burst slot period of 15th over 26 millisecond. A burst period is equal to a TDMA frame of 120 over 26 millisecond. And one channel is equal to one burst period per TDMA frame. 26 TDMA frame corresponds to one multi-frame. And 24 are used for traffic, one for control, and one is unused. There are also other functions such as slot associated control channel. If slot associated control channel does not have sufficient capacity, then the fast associated control channel is used by stealing one half of some bursts. So the control channel is used to communicate, for example, which data channel you are going to use, what is the cell phone ID, so on and so forth. And steering bits identify whether the one half slot carries data or control. Then we mentioned that each channel has 200k hertz. So 200k hertz equal to 270.8 kbps per A slot, which means that it has 34 kbps per slot. So after some calculations, we have 2.6 kbps per user after encryption and FEC overhead. FEC meaning forward error correction. So that's the, let's go back a little bit. You may notice that we have error detection, error correction code. So what that means is we have 9.6 kbps after encryption and forward error correction code. And then for rate voice coder, that vocoder means voice coder. So for rate voice coder is sampled at 64 kbps compared to 16 kbps. I mentioned that a 9.6 kbps is the minimum rate for voice, which comes from the Nyquist criteria. But now we are using a higher quality, meaning that the sampling rate is higher, so that the full rate vocoder is sampled to 16 kbps. It's in fact 64, which is a lot higher than 9.6. But the thing is, it does a little bit of compression. That's called source compression, and it's compressed to 16 kbps. So the subscriber I identify module SIM card contains a microcontroller and storage. It contains authentication, encryption, and accounting information. Owners need 4-digit PIN, and SIM cards can contain additional information such as emergency medical information. Mobile assisted handout. Mobile sends identities of 6 candidate base stations for an handout. Then MSC selects. So what that means is, if you imagine, let's come back to the cell structure. Let's say you are UE, you are in cell A. Then when you are moving around, you could possibly go into the boundary with another neighborhood cell. And when that happens, you actually uh, have 6 possibilities, right? Because your original cell A has 6 neighbors. So you have 6 possibilities to be chosen from. So uh, you will send signaling information to the MSC, and the MSC is going to check which one gets the highest strong signal from you and then select that one. So let's go back to the slide. So in this mobile assisted handoff, the mobile sends identities of 6 candidate base stations for handoff. That's what we mentioned in previous hexagon structure. Then the MSC will select one, and of course it's going to select the one with the highest, strongest signal. And also SMS, which is not that common nowadays because you have messengers already, and that's up to 160 characters sent over control channel and unicast or broadcast. Okay, so this is the cellular system, and one example is a, a particular cellular system the following characteristics: as cluster size 7, and then uniform cell size, user density 100 users per square km, and allocated frequency spectrum is 900 to 949. Bitrate requirement is 10 kbps uplink and 10 kbps downlink, and then modulation core rate 1 bps per hertz. and use FDMA, frequency division, remember that, and frequency division, FDD, and then how much uh, bandwidth is available per cell using FDD, how many users per cell can be supported using FDMA. Of course, then we can calculate uh, this by uh, divided by 200K, right? We mentioned about 200K. So you divide this, then you know the number of channels. And the cell area, uh, it has 100 users per kilometers, per square kilometers. So you can calculate the area, so on and so forth. So this is sort of a typical structure for the cell, and then you calculate the area, the number of users, and so on and so forth. Okay, I think that this is the end of the second hour. We the end of second hour. We're going to take a break and come back in a couple of minutes.